So hello, my name is Tianli, and I'll be presenting our paper on path sampling methods for differentiable rendering. So to start with some brief background, forward rendering seeks to produce realistic images given a set of scene parameters, whereas inverse rendering seeks to recover some scene parameters from given reference images. So for example, in the scene shown, we might want to recover the roughness of the ball given information about the rest of the scene. And we can do this by formulating inverse rendering as an optimization problem. So we want to find the value of the scene parameter that minimizes some loss function, which compares our rendered images with reference images. And differentiable rendering allows us to solve this problem by estimating derivatives and then performing gradient-based optimization. So in recent years, many advances have been made in differentiable rendering, and one important line of work aims to generalize differentiable rendering to deal with complex visibility-driven discontinuities, and our work does not deal with these, so we will only optimize parameters that do not affect visibility. And within this framework, an important algorithm that I'll refer to is the path replay backpropagation algorithm, which improved the time complexity of differentiable rendering from quadratic to linear. And also because the formulations for forward and differentiable rendering are similar, the path sampling methods used for forward rendering are often reused for differentiable rendering. However, this practice is suboptimal because the formulations are not exactly the same. So previous work has found that sampling methods tailored for differentiable rendering can greatly reduce variance. And to this end, methods have been developed to importance sample the derivatives of various BRDFs, which are used in surface rendering. And these methods can greatly reduce the variance of estimated derivatives, but a major limitation is that for global illumination, they require a recursive radiance estimate at each scattering event. And this branching causes quadratic time complexity. For volume rendering, sampling methods have been developed to estimate the derivatives of scattering parameters. And importantly, this method is compatible with path replay backpropagation so that it maintains linear time complexity. And this strategy for avoiding quadratic complexity is conceptually similar to ours, but only applies to sampling free flight distances for inverse volume rendering. So our work focuses on differentiable rendering for surfaces and can also be extended to volumes. So in our work, we derive a new theoretical formulation, which allows us to sample paths that are tailored to the integral computed in differentiable rendering. And our method is compatible with path replay backpropagation, so it maintains linear time complexity. And we also enhance our method using an adaptive pixel sampling procedure, which is useful for inverse rendering optimization. And our methods result in lower variance when estimating gradients, as well as improved inverse rendering performance. And I will show some of these results at the end. So now I will go over our new theoretical formulation, which we will later use to derive our new path sampling method. So we start with the path integral formulation of standard light transport. And under this formulation, the value of a pixel at the camera is an integral of contributions from all paths connecting the camera with the light sources. And we call this set of paths the path space. So for a single path between the camera and a light source, the contribution of the path is a product of contributions from each vertex along the path. And the standard approach for estimating this integral with Monte Carlo path tracing is to sample many paths, compute the contribution for each path, and then combine the contributions. So for this estimator to have low variance, the paths should be sampled from a distribution that is a good approximation of the integrand. And for surface rendering, this is usually done by sampling directions proportionally to the BRDF at each vertex. And the same strategy is usually used for differentiable rendering, but we'll see that this is suboptimal because the integral formulation for differentiable rendering is not the same. So now we take the derivative of the path integral with respect to some scene parameter theta, And we assume that the parameter does not induce discontinuities, so we can move the derivative inside the integral. And using the product rule, we obtain an expression that is the sum of a bunch of products, where each of these products is the same as the original contribution, except that one of the vertex contributions in the product is replaced by its derivative. So notice that if we use the same strategy as forward rendering and always sample paths proportionally to f, the resulting distribution is not necessarily a good approximation of this integrand. And our goal is to provide a sampling method that is tailored to estimating this new integrand. So to do so, we first rewrite this expression by calling each of these products a differential contribution, G, which gives this simplified equation. And here we visualize the differential contributions for an example path. We also call each of the pink vertices here the differential vertex of the path. And now for any path in the path space, we can obtain several corresponding paths in what we define as the differential path space, where each of these paths has the exact same vertices as the original path, but also an associated differential vertex. And using the differential path space, we can rewrite our previous expression as an integral over the differential path space, which removes the summation that we previously had. So we call the previous formulation the path space integral and our new formulation the differential path space integral. And both of these formulations are useful, so I'll refer back to the first one later in the talk. So our new formulation is useful because we can now importance sample paths from the differential path space proportional to the path's differential contribution as opposed to its standard contribution from forward rendering. And this is the main idea behind our method. So how do we importance sample paths from the differential path space? We want to sample paths where only one of the vertices is the so-called differential vertex. And at this vertex, the next direction should be sampled using a differential probability density, whereas at the rest of the vertices, the next direction should be sampled using the standard probability density. And for surface rendering, the standard PDF should be proportional to the BRDF, whereas the differential PDF should be proportional to the derivative of the BRDF. So now the problem is determining which vertex on the path should be the differential one. And because we do not know the length of a path in advance, we do this by making local sampling decisions in a manner that is similar to using Russian roulette for stochastically terminating paths. So at each vertex on the path, we first randomly decide with probability Q whether the current vertex is the differential one. If we decide that it is not, then we sample the next direction using the standard PDF, and we weigh the contribution of this vertex accordingly. If we decide that the current vertex is the differential vertex, then we sample the next direction using the differential PDF, we weigh the contribution accordingly, and then we set Q to 0 for all subsequent vertices so that there can only be one differential vertex at most on a path. And we note that Q is a tunable hyperparameter, and also that it is possible to sample an entire path without ever choosing a differential vertex. So now here is an example of the sampling probability for a full path. Here we assume that the differential vertex cannot be at the camera or the light source, so we start at the first intermediate vertex. So here we randomly decide that it is a normal vertex, and we sample the next direction from the standard PDF, which gives us the location of the next vertex. And then we randomly decide that this is the differential vertex, and we sample the next direction using the differential PDF. After that, we no longer need to sample a differential vertex. So we simply sample from the standard PDF, and for this example, the next vertex hits the light source, so the path ends. And we can compute the probability of forming this entire path by taking the product of the probabilities shown. And the total weight for the contribution of the path is 1 over the path probability. So now we have a method of sampling paths from the differential path space, but we can further improve by incorporating multiple importance sampling, which is a standard variance reduction technique used in rendering. So once we have sampled a path with a differential vertex, we can obtain several other ways of sampling this path by changing the location of the differential vertex along the path. So in this example, either the first or second intermediate vertex can be the differential one, and it is also possible that we end up with no differential vertex on the path. For each of these three possibilities, we can compute the probability of sampling the given path, and then we can sum these probabilities together to form a mixture probability. So now instead of weighing the contribution of the path by how we actually sampled it, we weigh the contribution using the path mixture probability. And this is similar to how MIS works in bidirectional path tracing, where MIS is used to combine sampling methods with varying camera and light subpaths. And we can also integrate our method with next event estimation, which is another standard technique that reduces variance by directly connecting paths to a light source. And to include next event estimation, we have to modify the MIS weight so that we also consider varying the location of the differential vertex along paths where the last vertex is sampled directly from the emitters. And this involves a slightly more complicated derivation, which we go over in the paper. So I have now explained our method for sampling paths from the differential path space and how to weigh their contributions. But there is one last thing to note. So going back to the formulations that we had before, we noticed that once we have sampled a path with some differential vertex, we can easily compute not only its differential contribution, but also the differential contributions of all its related paths in the usual path space. So in other words, even though we sample from the domain of the differential path space integral, we decide to compute the integrand of the path space integral because it is easy to do and gives us more information about a single path. So we can do this without introducing variance because each of the G terms matches one term in the MIS mixture probability. And lastly, we can implement our path sampling method by making some simple modifications to the existing path replay backpropagation algorithm, which lets us maintain linear time complexity and constant memory costs. And the highlighted changes here involve deciding whether to sample from the BRDF or its derivative and accumulating the MIS weight along the path. So the final component of our work is a pixel space adaptive sampling procedure, which is complementary to the differential sampling method that I have just described. So to motivate this method, remember that differentiable rendering is used for inverse rendering optimization, where we actually need to estimate the gradient of the loss function with respect to a scene parameter. And using the chain rule, the loss gradient is simply the product of two terms, where the first term is the derivative of the loss with respect to the image, and the second term is the derivative of the path integral, which we derived earlier. And the first term is sometimes called the adjoint radiance, and we can also move it inside the integral. And the estimates of the two terms need to be uncorrelated, so differentiable rendering algorithms estimate the adjoint radiance first using a separate rendering path. So now we notice that the adjoint radiance term appears inside the integral in the same way that sensor importance appears inside the integral for forward rendering. So we can then importance sample pixels based on their adjoint radiance when we estimate the full integral. And the full inverse rendering procedure then goes like this. In each optimization iteration, we render an image with the current parameters. We use it to compute the loss and adjoint radiance. And then we compute a weight for each pixel that is proportional to the absolute value of its adjoint radiance. And we then use these weights to sample pixels that we start paths from. And these paths are used to estimate the gradient that we need for performing optimization. We also recompute the sampling weights in each iteration, so the weights are adaptive and change during the optimization process. So now let's look at some experiments. First, we visualize the image gradient for this scene with respect to the mixture weight of the dragon's BRDF, which has diffuse and specular lobes. So the full gradient looks like this. And then to highlight the importance of global illumination for differential light transport, we also separate the gradient contributions from paths with a fixed differential vertex. So this is the differential contribution from the first bounce of light. This is from the second bounce of light, from the third bounce of light, and so on. And adding these separate differential contributions together forms the full gradient image. And here are two additional scenes that use a microfacet BRDF instead, and the gradients here are with respect to the roughness parameter. So now we look at how our differential sampling method impacts gradient estimation. For this equal time comparison, our method renders an image gradient that is visibly less noisy than standard BRDF sampling. And we can also evaluate this by estimating the variance of image gradients. So we do this by rendering the image gradient 100 times and then computing the variance of the gradients for each pixel. So here red means high variance and blue means low variance. And the improvement is subtle for some of the scenes, but we find that our method consistently reduces variance compared to standard BRDF sampling. And we obtain the lowest variance when using our method with multiple importance sampling and next event estimation. And because our adaptive sampling method is used for estimating the loss gradient, we cannot evaluate it by looking at the variance of image gradients as we did before. So instead we look at the variance of loss gradients, and for various scenes, we find that adaptive sampling consistently reduces variance by 1 order of magnitude compared to standard BRDF sampling. And when used with differential sampling, our combined method reduces variance by up to 2 orders of magnitude. So lastly, we find that our method's improvement in gradient estimation does lead to faster convergence in inverse rendering applications. So here we optimize for the mixture weight of the Dragon's BRDF, and the initial material is more specular, whereas the target material is more diffuse. The graphs show that our combined method, which is shown in dark purple, produces faster convergence than the baseline BRDF sampling method, which is shown in light green. And here we show the optimization process. And after optimization, our result looks visually closer to the target image than the result from BRDF sampling. And here is another example where now we optimize for the roughness of the sphere's microfacet BRDF. And again, we see that our combined method converges the fastest and produces a much closer result to the target than BRDF sampling. And please see our paper to find additional examples of optimization results. So to conclude, we introduced a differential path sampling method tailored to the integral computed in differentiable rendering. And we also introduced an adaptive sampling method to choose pixels to start paths from in each inverse rendering optimization step. And an important direction for future work is extending our differential sampling method to work for scenes that optimize more than one scene parameter or a spatially varying parameter. And this is more complicated because a sampled path might have a high derivative contribution for one scene parameter, but not for the other parameters. And our code is available on the project website, which you can find at the QR code. And thank you for listening.